Okay. Hi everyone. Hi, great. Okay. I hope everything was fine with you in the previous week. Is there any question about the previous sessions? No? Okay. Uh, so let's continue. We talked about the history of neural network, also neural networks with only one neuron. So we talked about perceptron, we talked about Adaline. Now let's move on to the, I think, yeah, sorry about that. It is, yes. Let's move on to the neural network with one layer, and then we will go to the fully connected neural network. So now one layer. So let's extend one neuron to one layer, and one layer might have multiple neurons, right? So in the lecture of training one neuron, we were introduced to the neural networks with only one layer and one neuron in it, right? Now in this lecture, we're gonna talk about neural networks with only one learnable layer. So they might have two layers, but one of them is only learnable. The other one is fixed, right? So one learnable layer, but possibly multiple neurons, okay? Multiple neurons in that layer. Two of these networks are radial basis function network, RBF network, and self-organizing map, or SOM. Okay. So first, let's talk about radial basis function network. A radial basis function, in short, we call it RBF, was first proposed in 1988. Okay, you can see the references 1 and 2 for that. And how is it, by the way? We have also RBF kernel. So in machine learning, don't confuse these things. The reason that they are all called RBF is that they are using Gaussian distribution in the, right? So RBF kernel has Gaussian distribution in it. RBF network also uses Gaussian basis functions. We'll see that. Okay, so RBF network has two layers, but the first layer has fixed weights equal to 1. Okay, so we don't learn the first layer. The second layer has learnable weights. Now the first layer connects the data, d-dimensional data, to m basis kernel functions. Okay, so do you remember, for example, when we say we have basis vectors for a space, we say that every point in this space can be represented as a linear combination of the basis vectors in the space. Likewise, we can have basis functions and represent any function as a linear combination of these basis functions. I think you have seen that a lot in different fields of science, specifically signal processing. Can you give me some examples of having basis functions and trying to represent any function as a series or of those basis functions? Give me some suggestions, examples. Have you heard of Fourier series? Fourier series. So we can represent a function as a linear combination of sine and cosine, right? This is called Fourier series. By the way, Fourier series, when Fourier wanted to, I don't know if you have heard of this, when he wanted to publish that, everyone rejected him. So he couldn't publish it as a paper. Finally, he decided to publish Fourier series and Fourier transform as a book, because in the book, books are not peer reviewed. You publish whatever you want, right? You just pay the publisher, or the publisher pays you, doesn't matter. But it doesn't have peer review. So he published that, and that became one of the most important books in the history of science. So yeah, that's interesting. Sometimes important papers get rejected. So yeah, Fourier series is one of them. So I think there are other transforms that you can use, like Laplace transform. These are all related. If you have passed any course in signal processing or digital signal processing, DSP, then you might have heard of all of these things. So in mathematics, it's very common that they write a function as a series of or as a linear combination of basis functions. One of them here is this. So if we consider the basis functions to be RBF kernel functions, and we'll see what they are. Let's denote them by phi ix, okay? Phi 1, phi 2 to phi m, okay? So we have m basis functions, and each of these is a function, right? So it takes x as input. Now so here it is. So we have x1 to xd, and each of these basis functions is taking all of the x1 to xd as input, right? As a vector. Also, the second layer connects the basis functions phi 1 to phi m to the output neurons. And let's denote the output neurons by yj hat. Hat means that it's estimated, predicted by the network, where j goes from 1 to k. So k is a dimensionality of output. Okay. D is a dimensionality of inputs, and m is a number of basis functions. Okay. The weight wij denotes the weight connecting phi ix to yj hat. Right? For example, this is w11 connecting phi 1 to y1 hat. This is w1k connecting phi 1 to yk hat. Okay. So as you see, we have two layers. The first one is fixed, and now the goal is to learn these w weights in the second layer. Okay. So the basis functions can be various kernel functions, such as these. So the most common one is the Gaussian distribution, hence the name RBF function. Because in the literature, this Gaussian kernel is also called RBF kernel. Okay, RBF function or RBF kernel. If you have seen kernel SVM, for example, one of the kernels that you can use for kernel SVM is RBF kernel with the same format. Okay, so phi ix is this. E to the power of minus squared L2 norm of xi minus mu I over 2 sigma I squared. What is this? This is exactly Gaussian distribution, but scaled Gaussian distribution. So it doesn't have the normalization factor behind it, right? And the other one is logistic or sigmoid function that sometimes they use. And this is the format of the logistic or sigmoid function. So 1 over 1 plus e to the minus something, you can see it as the sigmoid function. And this something here is minus x squared L2 norm xi minus mu I over 2 sigma I squared. Okay. By the way, sigma I squared is the variance, and mu I is the mean of the Gaussian distribution. Okay. Yeah, here we have said that, the mean and variance. Okay. At the first step, the means are found by applying a clustering method. So we have m basis functions, right? Such as k-means on what? On the training data with m clusters. So I have the data. I have the data set, training data set. So I'm explaining how to train the RBF network. The first step is to find, we need to have some mu's and sigma i's, right? To use these in these basis functions. But how do we find them? The first step is to find the means as the means of the clusters by applying some clustering algorithm on the data. For example, you use k-means. Do you know, is there anyone here who doesn't know what k-means is? I can explain if you don't know. Okay, so k-means is that basically it means I have a data set. I want to class. What do I mean by clustering? I want to group them into several groups. So I say the first thing which I think that comes to humans' mind for clustering is k-means. So it says that let's randomly say that these are set. Let's find the means of the clusters randomly. Okay, like assume I want to have 2 clusters. Okay, then I can assign each point to one of these clusters by the distance of the points to from the cluster centers. For example, this point has this distance from this center and this distance from the other center. Okay, and then the minimum distance shows which cluster it belongs to. For example, of course, if you do that, then these point, these, all of these will be in cluster 1. And these points which are closer to the next cluster center will belong to the cluster 2, right? However, it might not be perfect. The cluster centers might not be perfect. Let's fine tune them. Then how do we fine tune them? We can say, now that we have formed the cluster, we go the other way around. Let's update the cluster center by the average or the mean of the data points in this cluster. If you take the average, the cluster will be here. So I update the cluster center from here to here, and then I reassign the points again. If you do this iteratively, then the cluster centers will move to the right places, and it will cluster data well enough. Okay, this is one of the clustering techniques, which is the simplest ones. And as you see, sometimes you can see that there is no learning in it. So sometimes people say that k-means is not a part of AI or machine learning because you don't learn anything. Doesn't matter. You cluster your data somehow. One of the simplest techniques is k-means. You can use other methods too. So when I do that, then I can group my data into m clusters, and then let's assume the centroids or the centers of these clusters as the means of the m basis functions. Okay. Now, by the way, the variances of clusters also determine the variances of the basis functions. So each cluster has the variance, right? Some variance. I can calculate the variance. How can I calculate the variance of data? You know the formula for variance, right? So here, for example, yes. So you can say sigma I squared is 1 over n. Here n is the number of points in that cluster. Right? So you can use this. Now, RBF networks can be considered as additive models. Additive models are important things in mathematics, and I think in statistics. So an additive model, what is that? It was first proposed in reference 3. It maps data to a space with several basis functions, okay, and then tries to learn a weighted average of those bases. So consider some basis functions. An additive model maps data to some space whose basis functions are those several basis functions, and then tries to find the weights. By the way, you might be wondering, why am I using space with the basis functions? How does it mean? Because when I say space, you might think the space has some basis vectors. Agree? But in pure math, in functional analysis, you can have a space of functions. Okay. For example, Hilbert space is a space of functions. We don't want to go into the details of that. My knowledge is also limited in that area, but I'm saying that we have a space of functions, not just a space of vectors. Okay. Vector space is just a special kind of space. So additive model says that let's map data to some space, and that space has some basis functions, right? And then that data can be represented as a linear combination of those basis functions. Let me also find those the weights of the linear combination. So exactly this is an additive model. I'm writing yj hat as a linear combination of phi 1 to phi m with some weights, right? And these weights are learnable, okay? This is exactly an additive model in mathematics, okay? Consider now n data points together in a matrix X belong to Rk by n. Okay, what do I mean? So I think this must be, I think this is an error. This must be d by n, sorry. Okay, so now I'm considering d data points, a data set, agreed? A data set of data points. I stack them column-wise, so I will have d by n matrix X. Then, do you agree that I can represent this in matrix form? The matrix form of equation 3 is equation 4. Do you agree? If I have defined these functions, so W here has all of the W's in it, but it becomes a matrix. Why? Because I have Wij. I goes from what? You tell me. Let's go back to the figure. I goes from 1 to m, j goes from 1 to k, right? Therefore, I have m rows and k columns, right? This is W. What about phi? I can have that phi also becomes a matrix. Why? Because I have phi 1 to phi m, each of which can take x1 to xn. I have n data points, right? Each phi takes, let's go back and forth between the figure and the formula. Each phi takes a vector x, right? This is a vector x. Now this can be x, vector x1, the vector x2, until the vector xn, right? So as a result, my matrix phi becomes with a matrix with m rows and n columns, where each row is one of the phi's, but across different data points, and each column is one of the data points, but across different basis functions, m basis function. By the way, interrupt me wherever you don't understand anything. Okay, so now if you do that, what about W transpose phi? Phi here is m by n, W is m by k, so W transpose is k by m, so the whole thing becomes k by n. So y hat becomes k by n, where I have so what are these? So this every column is the predicted labels or outputs for one of the data points. Okay, because each data point has a k-dimensional label. Let's go back to the figure again. For a vector x, my output is k-dimensional. So I have, for every point, I have k-dimensional label, right? Predicted label. Therefore, I can have the matrix y hat with k rows for the dimensionality of labels and n columns for the number of data points. Agreed? Agreed. So now I have this equation 4 as a matrix form of equation 3. So what should we do? How to train? The first thing which comes to your mind. I have some predicted labels. I have some actual labels. What should I do? I should try. The best thing is that my predicted labels become as close as possible to the actual labels. So let's minimize the mean squared error, right? So exactly we are doing this. So squared Frobenius norm between y, which is the actual labels, and y hat is exactly mean squared error, right? Recall preliminaries for definition of Frobenius norm. Okay. So we have the actual labels k by n, and the predicted labels y hat k by n. and squared Frobenius norm of between these. Now let's replace y hat with equation 4. So y hat was W transpose phi, right? And what is my optimization variable? The matrix W, right? The weights of the second layer in RBF network. Okay, so now let's simplify this cost. Why? Because I want to take derivative, set it to 0. Because this is also an unconstrained optimization problem. So high school optimization. Take derivative, set it to 0. Okay, first let's simplify this. What is the formula for squared Frobenius norm? Squared Frobenius norm of desk becomes desk transpose desk, but I need to have trace because I need to make it a scalar, right? So trace of this transpose this, right? Which is here. Okay, now I apply transpose on the elements of the parentheses. So it becomes y transpose, and this one transpose. The order changes, is reversed. So I had phi transpose W and the rest as this. Now I have these 2 terms multiplied by 2 terms. I have 4 terms. So let's multiply the terms to each other. I have y transpose minus y transpose W transpose phi minus phi transpose WY plus phi transpose WY transpose phi. Okay. Now trace is a linear operator, so I can apply it on the elements. Right? Moreover, I can use the cyclic property of trace. You know the cyclic property of trace, don't you? Okay, if you don't know, just let me tell you once, because we use these a lot. So trace of A, B, C, assume A, B, and C are matrices. You can bring every matrix to the other side and do it repeatedly. For example, it is equal to trace of CAB equal to trace of BAC and BCA, and then again trace of ABC, back to where we were. Okay. So this is cyclic property of trace. Now, so here I have used cyclic property. How? I have brought this to this side and this to that side. Equivalently, for simplification, for cyclic property also goes the other way around. So I can say I bring this to the right hand side. Okay. Also here, I bring this to the right hand side. What about this one? For this, I need to do cyclic property twice. So phi transpose W, W transpose phi becomes phi transpose W, W transpose, then becomes W transpose phi transpose W. Agreed? So I will have this. Now, let's take derivative with respect to W. But so this one is a constant with respect to W, goes away. This one is linear with respect to W, is linear. How do we take derivative? So I think I didn't say this in deep learning course in this technique. Let me say it once. I have said it in the statistical machine learning course. So trace of W transpose phi Y transpose. Trace of W transpose phi Y transpose. Okay. Let's name this A, matrix A. Trace of W transpose A. Okay. So the derivative of this with respect to W, we know that this is a scalar and this is a matrix. So derivative of a scalar with respect to matrix is a matrix. And we know that this is either A or A transpose, but which one? Which one? Let's see. Here, assume W is 3 by 5. Assume. Okay. So this W transpose becomes 5 by 3. A becomes 3 by 5. When then the derivative of a scalar 1 by 1, because it has trace, with respect to a matrix 3 by 5, by convention, I say it must be 3 by 5. You can choose another convention and transpose it. But if you transpose it, you should transpose everything. Okay. My convention is easier. I say derivative of a scalar with respect to 3 by 5 should be 3 by 5. So if I do that, then here, A, according to my calculations, as W transpose is 5 by 3, this must be, A must be 3 by 5. Therefore, this is acceptable. This is wrong. Did you understand the technique? So I give fake dimensionality to the matrices, and then I see which is correct. Okay. By the way, I can make it more complicated. Rather than this, for example, assume I didn't name this 5y transpose as A. Then you could say I have several options. The derivative is either 5y transpose or y transpose phi, or you tell me phi transpose y. Some of them will be eliminated immediately. Why? Because the matrix dimensions should match in matrix multiplication, right? Some of them are nonsense mathematically. Okay, so they are removed. Some of them make sense mathematically, but how do we eliminate some and take some of them, some other? By these techniques that I told you. Give fake dimensionality to the matrices and check the dimensionality. Even you can use this technique even when W is a square matrix. Still, you can give fake dimensionality. 3 by 5, not 5 by 5. Why? Because if you give 5 by 5, we don't know which 5 it is, left 5 or right 5. Give fake dimensionality differently, like 3 by 5. Although you know, for example, that is a square matrix. Then you can filter out which one is the correct derivative. If you don't want to use this technique, feel free to go and check the derivative in the matrix cookbooks. There are 1,000 pages. And go try to find that specific derivative. Okay. So as I said, the derivative of this became A itself, right? This was A, right? Now, derivative of this using that technique that I told you, this is linear with respect to W, right? So is this, what about this one? It's a quadratic function with respect to W. So its derivative with respect to W must be 2 phi transpose W, right? And now set it to zeros. 2, 0 matrix, right? Because derivative of a scalar with respect to matrix is a matrix. Okay. Now rearrange the terms. So we know that these are equal to each other. So it becomes minus 2 phi y transpose. And the 2's cancel each other. 2 2's cancel each other. So we'll have this. Agree? This is a pain in the neck. Because I want W, right? Left multiply the sides by phi transpose inverse, by its inverse, to get rid of that. Then you will get this. Agreed? Interestingly, we could find W, our optimization variable, in a closed form solution. Why do we don't do the same thing for neural networks, for fully connected neural networks? We actually do. We take derivative, we set it to 0, but we can't find a closed form solution, so we use gradient descent. Here, we don't need gradient descent because we can find closed form solution. If we couldn't find a closed form solution, we had to optimize it iteratively, exactly as backpropagation does. Okay, but here, done in one shot, we could find the solution. Interesting. Okay, so this is the solution of RBF network. Now, there is a problem. Whenever you see inverse of some matrix, you should be scared. What if it becomes a singular? What if I can't take inverse of that, right? Then, so this is here. What is phi transpose is singular. What do I mean by singular? It means that at least one of its eigenvalues is 0. So it's not full rank, right? So you can't invert it. Then you can use pseudo inverse. inverse of matrix. Pseudo inverse, you can Google it. There are some formulas for that, but basically pseudo inverse is this. Let me, I don't have in, I haven't memorized it, so just give me, I can't memorize anything. So it's called Moore-Penrose inverse. Let me tell you what I mean by pseudo inverse. Assume AX equals B. Okay, so X is A inverse B, but what if A is singular? Okay, so I can't. So what should we do? Then I say I can say, just give me a second to figure it out. Yes. So rather than going in this path, I go in the other way around. So I say multiply the left, multiply the sides by. Give me a second. Give me a second. Transpose A inverse A transpose A. Yeah, I think I'm right. I think I'm right. Left multiply the sides by A transpose. Yes, yes, I'm right. Okay, left multiply the sides by A transpose. Why do we do that? What is the philosophy behind that? Don't memorize these formulas. Understand the philosophy behind them. Why do I left multiply the sides by A transpose? Because I know A might be singular, but A transpose A is not. Okay, here in this case, I think A is a long matrix. So A transpose A becomes a small matrix, and I know it is full rank. Okay. Then this, I know it's full rank, so I can take inverse of this. So I left multiply the sides of this by inverse of that. Did you understand? I'm left multiply the sides by inverse of this, which I'm sure is full rank. This is called pseudo inverse. They denote it by A dagger. Okay. By the way, we have a similar formula if A is wide, not long. Okay. If A is wide, you tell me, what should I do? Oh, okay, okay. That's another technique. Good that you raised that. I will also talk about it. That's a good point, but that's not the answer to this question. What if A is like this? Is wide. So of course, if A is wide, then I know that A transpose is full rank rather than A transpose A. So I should kind of generate some A transpose. How? Can you tell me? I need to think about it. But if you rearrange this using linear algebra, then you can, by left multiplying and right multiplying the sides, you can. I need to think about it, but there is no time for it. You can make A transpose, and then you left multiply the sides by A transpose inverse. Okay. So the other formula that I'm looking up on Wikipedia is this: A dagger for when A is wide is A transpose inverse. Okay. So basically you will end up with something like this: A transpose inverse B. You call it A dagger. Okay. Another point which you mentioned, and that's interesting, is that there is another technique to deal with the singular matrices, and that is a hack that we can use, and that's used a lot in machine learning. Let me add a page. So what did I have? I had that W equals phi transpose inverse. W equals phi transpose inverse phi Y transpose. And our worry was that what if this is singular, right? By the way, in pseudo inverse that I talked about, I assume phi transpose is matrix A. Okay, the whole thing is matrix A. I assume that. Okay, then another technique is that you can approximate it by phi transpose plus lambda I inverse phi y transpose. So you add lambda I to that, where I is the identity matrix and lambda is a small positive number. If you do that, what does it do? What?
It wouldn't be zero. It's always a very small.
Yeah, exactly. So when you do that, there will not be any zero eigenvalue. So it means that when you strengthen, according to linear algebra, when you strengthen the main diagonal of the matrix becomes full rank. Okay. So it won't be singular anymore. But it's a hack. It's an approximation. It's not exact. When lambda equals 0, it's exact, right? But therefore, lambda should be as small as possible. Not too small to become singular, but not too big to become inaccurate. So there is a trade-off between accuracy and being full rank. Okay, that's also another technique. So yeah, we have various techniques to deal with inverse in machine learning. Okay, now where were we? Oh, yeah. Yes, student, we talked about these. So this is a formula. Now let's use it in test phase. So training is over. Training of RBF is over. In test phase, how should we predict for some input? For some input X, what should I do? First, I should calculate phi. How was the matrix phi calculated? Let's go back. Here is matrix phi, which has X in it. So phi, you feed the X's as input to your kernel basis functions, such as RBF functions. Then you can form this matrix phi, right? Then I can assume that my y hat is W transpose phi. W is already learned in the training phase, right? But why am I allowed to say that? Why is y hat why does it equal to W transpose phi? What were we minimizing? The difference between W and Y transpose phi. So Y is supposed to be phi, W transpose phi, right? So I can use W equals Y hat equals W transpose phi. So this is exactly equation 4, right? And I'm trying to minimize the distance of this with the actual labels. Okay, so I can use it, and then I replace W with equation 7. If I do that, then I can apply transpose on the elements. Therefore, I have this Y transpose becomes Y, phi transpose, then phi transpose inverse transpose, right? Inverse transpose, and then phi. But note that, yes, I think, yes. Now, what happens from this step to this step? Can you tell me? I'm applying this transpose in the parentheses. We know that transpose reverses the order. So both transpose and inverse can reverse the order. What do I mean by that? So when you have AB transpose, it becomes B transpose A transpose. When you have AB inverse, it becomes B inverse A inverse. Okay. Here I'm applying transpose on the elements inside. So it becomes phi transpose, which is phi, then phi transpose. This basically means that phi transpose here is symmetric, right? Okay. RBF network is over. Okay. I know it's very simple, but they were very excited about it, because they said that we can approximate any function using a linear combination of RBF functions, right? and that has some background in functional analysis. So they had some mathematical proof for that. This okay, it's a breakthrough. Okay, but they were not thinking that maybe later we can have multi-layers, just not one layer. Self-organizing map. That's also another fundamental network with one layer. So self-organizing map, or SOM, is a neural network with one layer. It is used for unsupervised clustering. So it's used for clustering. Where the name self-organizing comes from. Why? Because clustering, do you remember preliminaries? Clustering tries to figure it out itself by the pattern of data. So it self-organizes itself. Okay. It was proposed by Tova Kohonen in 1982. Therefore, it's also called Kohonen network. It is one layer connecting the data, d-dimensional data, to k neurons. Okay, so something like this figure, the left-hand side. I'm connecting d-dimensional vector to k neurons with some weights, where wij connects the xi to neuron j, right? Then, yeah, wij denote the weight connecting xi to the jth neuron. Each neuron represents a cluster. Okay. So self-organizing map trains the weights. Sorry. Self-organizing map trains the weights to cluster the input data to one of the k clusters. So k, which is a number of neurons, is also the number of clusters, right? Do you remember we talked about k-means? So this is another clustering algorithm. Okay. The neurons can be put in 1D or 2D structure. So sometimes when they want to make it a cool visualization, they put neurons in a 2D structure. Doesn't matter. 2D, 3D, 1D. Okay. There are some neurons. We can put them on the plane. So every neuron has a neighborhood around it in the 1D or 2D structure of neurons. So for example, in 1D, the neighborhood of neuron 2, for example, is D, some neurons around it. In 2D, then you have both rows and columns, right? So it becomes like a square. This neighborhood is decreased gradually during the training phase. So it's initially big, then it's decreased gradually. Let nj tau denote the neighborhood of the jth neuron at iteration tau. So it's an iterative algorithm, right? nj tau is the neighborhood of jth neuron at iteration tau. Okay. Now step 1 of training. Initialize all weights to small random values. Of course, because it's an iterative optimization, so we need initialization. Then set all neighborhoods. So we have j neighborhoods, right? Because we have j neurons. To half of the neuron structure grid. So initially, the biggest neighborhood that we set for each neighborhood is half of the neighborhood structure. What do I mean? For example, in 1D, I have k neurons. So neighborhood is k, neighborhood length is k over 2. In 2D, if I have, for example, whatever we say, square root of k by square root of k neuron, then my neighborhood becomes square root of k over 2 by square root of k over 2. Set the initial learning rate to a number in range 0 and 1. Okay, these are suggested by the author of the algorithm. By the way, we need learning rate because we're gonna use optimization, right? Now step 2 of training. Select one of the input data points, x, and what do I mean by select one? Because I have a data set, right? Select one of them, either randomly or in order, doesn't matter, and feed it to the network. Okay, then select the winning neuron z by this. So what is equation 9 doing? It says that So xi is the ith feature of the x, right? Then I can, what is this? This is the length between the vector, the xi and wij. Here, I think, just give me a second. There is no need to use L2 norm because these are scalars. But doesn't matter. We can say, you can see it as xi minus wij to the power of 2. The only thing which matters to me is that the sign doesn't, I don't care about the sign, okay? Then, so xi and wij, I want them to be as small as possible. What do I mean? My ideal case is that wij is as very similar to xi, okay? So I want in SOM, I want my weights to be similar to my inputs. Then I sort them. Then I get the smallest. So the J, which neuron has the smallest cost? This is the cost. Which neuron has the smallest cost? What do I mean? Which neuron has the smallest has the closest Wj to xi? Agreed? Which neuron? Let me repeat. Which neuron has the closest, most similar wij to xi? I denote it by z. So z is the index of that neuron. Then step 3 of training, update the weights of the neurons in the neighborhood of the winning neuron z. So here we found the winning neuron, which was z. One of the neurons won. Okay. Now I update the weights of that. The weights connecting to that winning neuron. How? In this way. So if J is in the neighborhood of the winning neuron, update the weights for that in this way. Otherwise, don't update it. Basically, let me recap. I feed some input to my network. I get which of the weights is closest to the input. Then it determines the winning neuron. That winning neuron has some neighborhood around it, right? For all of the neurons in that neighborhood, I update their weights. Did you understand? For all of the neurons in the neighborhood of the winning neuron, I update their weights. Okay. And how do I update that? Using this. Let's analyze it. Does it make sense? This update.
So what should the winning is to the weight?
Because so if you see this update is also exaggerating this. Do you agree that when I input my data to the neural network, then it's actually very closer to one of the weights? Do you agree? Okay. And the reason that it wants to find the closer weight to that or closer neuron to that input is that I want to do clustering. I want to see which neuron is closer to which data point. So you can see the neurons or their weights as representatives of the clusters. Which cluster is which cluster is more similar to that point? No, you can see. So you can see the neuron as the center of that cluster. Okay. So the weights of the neuron determine that cluster, and then you say which neuron is more similar to this data, so I can assign that data to that cluster. I agree that it's a bit, you need to imagine it a bit. You need to, but when you understand it, you'll see that it makes sense. So basically, I want to cluster my data points using the neurons. So I need to assign each data point to one of these neurons, right? Assume these neurons are the representatives of the clusters. So whenever a data point comes, I need to assign it to one of the neurons. How do I do that? Using equation 9. I see which weight is most similar to that data point. Then I say that this neuron says I want Now let me update all of the neurons in my neighborhood. Okay. Neighborhood, we set it initially big, like what I said in step 1, and then we decrease it gradually. I will tell you how to decrease. So, but why? How do we update it? Using equation 10. As you see in equation 10, we exaggerate it. We exaggerate. So what do I mean? I want this to be closer. So Wij was close to the xi. Now let's make it closer. And also its neighbors, right? By the way, you understand when I'm doing that, I'm also updating my neighbors. It means that the neurons or the clusters which are closer to each other in the structure of 1D or 2D, they are actually closer in pattern 2. When I do this, then there is a semantic relation between the clusters as well. When two clusters are close to each other in this plate, it means that they are actually closer to each other. But when they are farther from each other, their patterns also are far more different. Okay. So when I do that, then step 4 of training, decrease the learning rate and neighborhoods. So learning rate is decreased. Why? Because exactly as in deep learning, we explore first more, because initially we are not close to the solution, so we jump with higher steps. But gradually, I'm assuming that I'm getting closer and closer to the solution, so I decrease my jump step, so I exploit more. So there is exploration versus exploitation in optimization. Initially, I explore, then I exploit. Okay, that's the reason. And as you see, this idea has been remained until now in deep learning. And this now, let's halve the neighborhood at every iteration. Okay, so we decrease the neighborhood. Step 5, increase the iteration index and go to step 2 and repeat this procedure. So gradually, the neighborhoods become too small that become one neuron, and the neurons have been, the weights of the neurons have been updated so they can cluster data. Now in test phase, when a data point comes, you can see, you can use equation 9, see which weight is closer to that data point, so you can assign that to that neuron, and that winning neuron determines the cluster index of that data point. Agree? By the way, I understand that this is hot, temperature is hot, but I don't know what to do. But sorry about the temperature of the class. I think we can open that door. Okay, so acknowledgement, some slides of this slide deck were inspired by teachings of Professor Ali Qudsi at the University of Waterloo, Professor Fakhri Karay at the University of Waterloo, and Professor Saeed Bagheri Shouraki at Sharif University of Technology. So these are the references. Now let's move on to the next topic. Any questions? No? Okay. So, but we halve it. Why halve? We need to decrease it somehow. Why halving? The author suggested that. Maybe empirically they have found out that halving works. No. Until it becomes one neuron itself. Okay. So, by the way, self-organizing map has a lot of variants. Okay, this is the main idea. There are books on self-organizing map. Okay, so this is the main idea of SOM. Now, a neural network with one layer is finished. So let's move on. Let's increase the number of layers. Let's have multiple layers, and that's fully connected neural network. Okay, so a fully connected neural network is just a stack of layers of neural network. Okay, so you stack several layers, where in every layer, all neurons of the previous layer are connected to all neurons in the next layer. Hence the name fully connected neural network. Fully connected means that all neurons of the previous layer are connected to all neurons of the next layer, but the neurons of each layer are not connected to each other. Okay. And every layer of the fully connected neural network is called a fully connected layer. Every layer in this network is also called fully connected layer or a dense layer. Different libraries they are named differently. And each neuron in the fully connected neural network is a perceptron neuron. So when you zoom to each of the neurons in this network, it becomes a perceptron network, which we discussed in the previous session. Why? Because simply perceptron won over the competition over Adeline. Perceptron was developed in Cornell University and Adeline in Stanford. So Cornell, in terms of neural network, at least Cornell won. Okay. Otherwise, nowadays we would have multi-layer Adelines or Madelines nowadays. That is why this network is also called multi-layer perceptron or MLP. MLP was proposed by Rosenblatt in 1958 in the same paper as perceptron, but at that time they were aware how to train it at least very well. In that paper, he proposed an MLP with 3 layers. Okay, with 3 layers. So this figure is a 2-layer multi-layer perceptron. By the way, usually we call this input layer. An input layer, you can see them as data features. Okay, so the neurons can be the data features. And you have this as output layer, which gives you the predicted outputs, right? And the rest as hidden layers. So these are hidden layers. Sometimes this is a bit confusing in the literature. Sometimes I think they consider the input layer as one of the hidden layers. Sometimes they don't. Doesn't matter. The mathematics behind that is important. Okay. Okay. Each neuron in the fully connected neural network is a perceptron neuron, as we talked. So it has, let's recall perceptron. So it must have summation of the outputs of the previous layer multiplied by the weights of the previous layer. This is exactly what we had in perceptron, right? So we have WIL times ZL. Assume ZL is the output of the neurons from the previous layer, right? Then I multiply them by the weights WIL, where WIL is the weight connecting the 11th neuron in the previous layer to the ith neuron in this layer, in the next layer, right? Then I sum them up, so over L, which is the number of neurons in the previous layer, okay? Then I denote it by AI here. AI, now I feed AI to some activation function, sigma I, right? Sigma I. And this sigma I can be a nonlinear activation function. So then the output of the activation function becomes Zi, which is also again used as in the summation of the next layer. Okay. If I don't have any activation function, then Zi becomes AI. But we have to have activation function usually. Why? I tell you now. Okay. Every layer in the fully connected network can be seen as a linear projection followed by an activation function. Why? So consider this X. Let it be D by 1. A D-dimensional column vector. Okay. Then what do I have here before activation function? Here I have W1 transpose X. Okay, I will tell you why. So X is D by 1. W1, assume is, you tell me, something by something. But can you tell me what is the dimensionality of W1? Give me suggestions. If that's wrong, that's fine. My input assume is D-dimensional. What is the dimensionality of W1? W1 is a matrix, by the way, right? Because it has some weights connecting the previous layer to the next layer. But can you tell me the dimensionality of W? By the way, try to understand this slide very well. I heard that although it's very simple, but if you don't understand it, you can't understand neural network. They have asked these similar to these concepts in Google interviews. Okay, for interviews for Google, I have heard. But I think that's a very simple concept. What? D by what? So why 1? But D by, that's correct. So it has D rows. Why? Exactly. Exactly. So because here I have D neurons, right? And D by something, but you said 1. Why? Here I might have multiple neurons. Let's call it P. Okay. If my layer is going down, so if my layer is connecting more neurons to smaller number of neurons, then P is less than D. If it is going up, so if the previous layer has less number of neurons than the next layer, then P is greater than D. Okay. So W1 is D by P. Now let's analyze W1 transpose X. W1 transpose is what? P by D. X is D by 1. So the whole thing is P by 1, which is exactly the vector here. Right? Now recall preliminaries. What is W1 transpose X? According to the preliminary. Exactly, that's a linear projection of X onto the columnar space of W1. Agree? W1 transpose X, according to the discussions in the preliminaries that we had, is a linear projection of X onto the columnar space of W1. Then I feed this p-dimensional vector to the activation function of the first layer, sigma 1. Then, so here, after activation function, I have this. By the way, this is also p by 1, because I apply activation function element-wise, okay, on the p-dimensional vector. So sigma 1 W1 transpose X is also p by 1. Now, what is dimensionality of W2? For example, it is p by k, right? Here in this case, k is greater than p, right? Now, if that's the case, what is the dimensionality of W2 transpose? K by p. Let me write it cleaner. It's k by p. So the whole thing here is k by 1, which is exactly the vector here, k by 1. Now I feed it to the activation function of the second layer, sigma 2. Again, this is applied element-wise. So this is also k by 1. What is the dimensionality of W3? It is k by something such as L. Okay, where L is the dimensionality of output. The labels predictedly, whatever. Then W3 transpose becomes L by K. So the whole thing becomes here. The whole thing becomes L by 1. And after applying the sigma 3, which is the activation function of the last layer, that's again L by 1. This gives me the output, predicted output. Agreed? Okay. Now, first off, why do we need activation function? Assume I don't have the activation function. When I say don't have activation function, I mean get rid of sigma 1, sigma 2, and sigma 3 in equation 3. Then do you agree that you will have, what do you have? You will have exactly this equation, right? W3 transpose, W2 transpose, W1 transpose X. Do you agree that as W3 transpose is a linear projection onto the column space of W3, W2 transpose linear projection onto the column space of W2, W1 transpose linear projection onto the column space of W1. So all of them just are linear projection. When you have linear transformation of linear transformation of linear transformation, the whole thing is also linear transformation. So I can replace these with V transpose, right? I can assume that X is projected onto the column space of V, where V is W1 times W2 times W3, because the V transpose must be W3 transpose, W2 transpose, W1 transpose, right? And what is this V transpose X? It's linear projection of X onto the column space of V. So the whole network collapsed into linear projection. So if you don't consider here, for example, we have a 3-layer neural network, right? If we don't consider any activation function, any nonlinearity between them, the whole network reduces to 1-layer neural network without any activation function. Why do you need 3 layers? It becomes 1 layer, equivalent to 1 layer. And also, when you don't have any activation function, what happens? Also, the network becomes a linear operator, a linear function, right? So how does it deal with nonlinear pattern of data? Assume you are doing a classification problem by neural network, and you have moons data such as this. How do you separate them with linear border, decision boundary, right? They are non-linearly separable. So you have to have a nonlinear model for that. And the whole art of neural network, the whole benefit of neural network is to handle nonlinearity. Otherwise, we have good enough linear methods, right? So you have to insert some nonlinearity to your network. This is the requirement for activation functions. Why? Collapse. So I mean, you can assume W3 transpose, W2 transpose, W1 transpose as V transpose. So you collapse 3 linear projections into 1 linear projection, or reduced, or relaxed. What's a different names for it, right? It reduced to 1 linear projection, right? What word is it? So nonlinearity is important for handling nonlinearity. Now another, so let me write it down, nonlinearity for nonlinear pattern. Also, removing activation function is equivalent to assuming that the activation function is a linear function. Okay, if you assume your activation function is a linear function, what do I mean by it? I mean this. Whatever it gets, it outputs it's that thing or multiplied by some scalar, right? Then it doesn't have any impact because it can be absorbed into the weights of the neural network, right? So linear activation function basically means that you are not using activation function. That's also another thing which I wanted to let you know. Another, so one thing was this, one thing was this, one thing was this, one thing was this, another thing which is very important, I believe. You can see that there are a lot of philosophies behind that. Okay, why are neural networks working very well? Why are they working very well? What is the reason behind that? before development of neural networks, at least deep learning, we had different algorithms in machine learning, right? In the statistical machine learning. Many of them, for example, many of them were in the field of dimensionality reduction. So dimensionality reduction is a subfield of machine learning. What does it do? It extracts features and reduces the dimensionality of data. It compresses data, but in this compression, it also improves the pattern of data. For example, when the data classes are nonlinearly separable, it separates them by this transformation and tries to make them linearly separable, at least as much as possible, right? Or if data points of the same class are far away from each other, it pushes them toward each other. And also it pulls away the dissimilar points, right? So it performs some actions, some pre-processing for the actual classifier or regressor to work better. That's dimensionality reduction, a big area in machine learning, a big area. Another area in machine learning is kernel, right? For example, it's the other way around. You increase the dimensionality, right? So for example, I will talk about it in a statistical machine learning course. So for example, when you have kernel SVM, what does it do? Let me add the page.
Here, the same meaning as kernel function you mentioned in the first slide.
No. So by the way, kernel is used with different names in different fields of science. For example, you shouldn't confuse this. For example, we have kernel in linear algebra, which is related to column space. We have kernel in, I think, distributed computing. We have kernel in various fields of science. Okay, in machine learning, what we mean by kernel usually is the transformation to the higher dimensionality and Hilbert space. Also, sometimes, such as in RBF neural network, we call that function also kernel, right? Why did we call that kernel function? Because you can use that in kernel matrix too. Okay, so sometimes the basis functions in machine learning are also called kernel functions, but they're basically the same thing. So in summary, I can say whenever in machine learning you hear kernel, unless specified, it means that the kernel function, and this kernel function can be used for calculating kernel matrix. Okay, more details I will talk about in the statistical machine learning course. But basically, when you want to calculate a kernel matrix, you need to calculate it by some kernel function. And one of those kernel functions is RBF kernel, which we just saw in RBF network. Okay, don't confuse these things altogether. We have kernel in signal processing for filter. Don't confuse, these are different things. Okay, what were I saying? What was I saying? Oh, okay, kernel SVM do. So I was saying that assume I have two nonlinearly separable classes in 2D. Okay, then I can increase the dimensionality maybe to 3. So assume I bring the stars up, okay? Then they become linearly separable now because they can be separated by a plane, right? This is called kernelization in machine learning. There are at least 2 ways to do that. One of them is kernel trick. The other one is kernelization by representation theory. I will talk about both of these in a statistical machine learning course. It's not related to deep learning. But why am I saying this in this course? I will tell you why. So in kernelization, we are increasing the dimensionality in machine learning. Hopefully, it makes the pattern of data easier. Also, dimensionality reduction reduces the dimensionality, hopefully, to make the patterns easier. Now let's combine these 2 ideas together. Okay. Sometimes we decrease the dimensionality, sometimes we increase the dimensionality. When in a neural network, when I go from more neurons to smaller number of neurons, I'm kind of doing dimensionality reduction. When I'm going from smaller number of neurons to higher number of neurons, I'm kind of doing kernelization. And as you see, these dimensionality reduction and kernelization also are have nonlinear functions. So it becomes nonlinear because of nonlinear activation functions. So it becomes nonlinear dimensionality reduction, nonlinear kernelization. All right. Now let's stack several dimensionality reduction and kernelization methods together, and let the network learn it by its own using optimization. Now, can you imagine what a monster it becomes? It's just neural network. You can see it as a stack of different machine learning algorithms, right? When you are using simple machine learning, you're using one algorithm. Neural network is when you have a neural network with 10 layers. It's kind of a combination of 10 algorithms. So it becomes a monster, and that's why it is working very well. Okay. Now, activation functions. There exist various activation functions. Some of them are these: linear or identity activation function. So basically, it means that no use of activation function. So sigma A equals A, and here it is. I'm plotting it here. So its domain, so its output is between -infinity to infinity. So there is no range for output of activation function. And its derivative. Why am I talking about the derivative? Because we need the derivatives of activation functions also in the backpropagation and gradient distance, right? And these derivatives will come in the chain rule of the derivatives. Agreed? By the way, this is just this is a list of most important activation functions. For a full list, you can see at least there is a good Wikipedia page for activation function. That's a good list you can see. So its derivative is 1, of course. Derivative of this is 1 with respect to A. By the way, A is the input of activation function, right? Which is the output of the summation. We can have binary step. What is this? If A is less than 0, let it be 0. Otherwise, let it be 1. So it's like this. Makes it binary, right? And as you see, it's either 0 or 1. And I think it's better to say this. Yeah, it's either 0 or 1. And its derivative at 0, it's undefined. But if it's not 0, then it's 0. Because in all of these areas, the derivative is 0. Then sign or signum function. What does it do? If A is less than 0, it returns -1. If A is greater than 0, it returns 1. This is exactly sign, right? Sign function. And this is also -1 and either -1 or 1. Its derivative everywhere is 0 except at 0. Okay. But these are not usually used. Well, this linear function is used a lot in some cases. When do we use linear function or no activation function? Of course, not everywhere. If we use linear activation function or no activation function everywhere, it collapses into one linear projection. Some layers we need no activation function. When do we need what layers? So one of the benefits of activation function is what? Let me write it down. One of many benefits. One of the benefits is activation function. For example, one of benefits is nonlinearity, right? To handle nonlinear patterns of data. Another benefit, in other words, let's kill several birds with one stone. Okay. Another benefit is what? I want to put a cap on the output of my layer. So I don't want my output to be in anywhere. I want to put a cap on output. So for example, I want this layer to output values between 0 and 1. So put a cap or range. Cap or range on output of the layer. Agreed? And you can find out other benefits too, but at least these two are very important. Now you tell me, assume I have a regression problem. I know that my labels are supposed to be between 0 and 1. So I put in the output layer, I put some activation function whose output is between 0 and 1. Assume I know that it's between minus and 1 and 1. So I put a activation function whose output is between minus 1 and 1. We'll see them in a few slides. Okay. What if there is no range for my regression problem, for my labels? They can be between minus infinity to infinity. I don't have any. Then I shouldn't put any activation function in the last layer. Of course, agreed? Otherwise, for example, it wants to become, the label wants to become 10, 10.5. I have put a cap between 0 and 1. It can never reach 10. Okay. So that's one thing. Logistic or sigmoid function. At least we saw that in logistic network. Sorry, logistic regression for one neuron, right? So this is logistic or sigmoid function, and we talked about it. We saw that this was initially proposed for modeling the population, right? Okay, so, and this is actually between 0 and 1. This is logistic or sigmoid, right? Limit this where a goes to minus infinity and to infinity. It will go to 0 and 1 respectively. Okay, then it's between 0 and 1, and its derivative, just simply take the derivative of this with respect to a, and you will see that you can write it as sigma a times 1 minus sigma a. So its derivative is very interesting. Its derivative is itself times 1 minus itself. Okay, the other one is hyperbolic tangent or tangent h, tan h. So what is that? It's this, e to the power of a minus e to the power of minus a, and in the denominator is the same but with plus. So of course it becomes between minus 1 and 1. Okay, and here it is. I've drawn it, and its derivative is this. If just simply take derivative with respect to a, and you will find out that it is equivalent to 1 minus sigma a squared. So derivative of this hyperbolic tangent, it becomes 1 minus itself to the power of 2. Okay. So whenever I want the output of my layer to become between 0 and 1, I use logistic function, sigmoid function, right? And when I want it to become between minus 1 and 1, I use hyperbolic tangent. Agreed? Why is this very used a lot? So logistic function is one of the widely used activation functions, especially in the last layer, because I want to make it between 0 and 1. Why is it important for me to make it between 0 and 1? Sometimes in my regression problem, it's already between 0 and 1, and I use that. But there are other cases that I actually need the output to be between 0 and 1. Probability. I want to output probability, and the probability is between 0 and 1. Okay, that's another thing. So probability. Another thing is that what if my output is between some a and some b, where a and b are some scalars, right? What can I do? I can use either logistic function or hyperbolic tangent as input, and then do some transformation to map 0 and 1 to range a and b, to map minus 1 and 1 to range a and b. I think it's very easy, right? Just using some transformation, you can map some range to some other range. Do you agree? Do you know how you should do that? Let me tell you. These things that I'm saying, although they are not much theoretical, but they're useful for industry. Okay, so just give me a second to think. For example, I have between 0 and 1. Okay, my range is between 5 and 10. What should I do? Either in the training, I map between 5 and 2 to 0 and 1, and I do this. So of course, in the training, I have to do that, right? But in the test, I have to map it back. Okay, then how can I do that? I simply can, let me think. So 10 minus 5 is 5. The range is 5. Therefore, I can multiply this by 5. So it becomes between 0 and 5. Then I can add 5 to this. It becomes between 5 and 10. Agree? So it's simple multiplication and plus, right? Okay. Another one is Gaussian or radial basis function. And what is that? It's this. It's just similar to Gaussian distribution, right? Centered at 0 here. You can also change the center, the mean, if you want the output of your layer to have some mean. Then, of course, it outputs between 0 and 1 because of this formula. It's between 0 and 1, right? And its derivative is this. If you take derivative of this with respect to A, is this. Okay. For example, you can kind of see that. Can we say that? No. I wanted to say that RBF network has RBF activation function, but I think we can't say that. Anyways, soft plus. It was proposed in 2011. It's this. What does it do? It's a natural logarithm of 1 plus e to the power of a. It's between 0 and 1. Its figure is here, shown here. Okay. And its derivative is this. Very simple. They usually propose activation functions whose derivatives are easy to calculate because we need to calculate the derivatives. And so, of course, if you want some output to be positive only, non-negative, then you can use soft plus, right? For example. ReLU is the most widely used activation functions nowadays for hidden layers. For output layer, they usually don't use that. Okay. For the hidden layers, they actually use mostly ReLU activation functions. So hidden layers. And it's this. Here I have shown it. For a less than 0, it's 0. For a greater than or equal to 0, it's a itself. It's with a slope 1. So it's basically the function of max 0 and that input, right? And so it's between 0 and infinite. And its derivative for negative is 0. For positive values, it's 1. For 0, it's undefined. Okay. But why is ReLU so important? Can you guess? We will talk about these in more details in a few lectures, I think, when we will talk about regularization. But can you tell me why ReLU is important? I kind of gave you a hint. You can see it as a regularization technique. Okay. What does it do? What does this function do? Yeah, but so this part does nothing, right? This part is like a linear function. Does nothing. Yeah, so exactly. The negative values are penalized, but how much? They become 0. Okay, they are pushed to 0. What does it remind you of? Makes it sparse. Okay, I don't know if you have had a chance to watch that regularization and overfitting lecture that I asked you to watch in the announcements of the course link. But L1 norm regularization, for example, makes data sparse, makes the algorithm sparse. It puts a lot of dimensions to 0, sets them to 0. Here, it sets half of the values which are negative to 0 exactly. So it makes it sparse. And according to the betting on sparsity principle in machine learning, and also Occam's razor in logic and philosophy, sparsity usually works well. Okay. Why is it? Because in output layer, we usually need the negative values too. So ReLU is used a lot. And by the way, ReLU was one of the reasons that nowadays that we don't use initialization of neural network weights by restricted Boltzmann machine. One of the reasons for extinction of restricted Boltzmann machines and deep belief network is ReLU. The other one was dropout. These two made it possible for us to make the neural network deep. So it also helps with vanishing gradients and gradient explosion. Okay. So this and dropout possible to make network deep. Because it's a regularization technique. You can see ReLU as a regularization technique. Regularization is not just weight decay. We have various techniques for regularization in deep learning. We will talk about them. ReLU, you can see them as regularization technique. Now, the other one, now after ReLU, some people noticed one flaw with ReLU. And what that was? Non-smoothness of here, right? So they said, let's resolve this non-smoothness of ReLU, and we have various variants for this resolving. So one of them is exponential linear unit, or ELU, proposed in 2015. It's this. Its plot is here, shown here on the right-hand side. And as you see, it goes a bit in the negative side, but it stagnates at minus alpha. Okay. So it's between minus alpha and infinite. Of course, alpha should be a small positive number. And its derivative is this. And as you see everywhere, it is a smooth. Okay. The other one was leaky rectified linear unit, or leaky ReLU. Leaky ReLU addressed another problem with ReLU. So sparsity, you can see it as both good and bad. It's like a scissor. Okay. So it makes it sparse. It's good because of betting on sparsity principle, but we are ignoring the negative values completely. That's another problem with that ReLU. So let's make it leaky ReLU. Let it leak a bit for negative values, right? So then for negative values for a small slope, let it leak. Therefore, it's again between minus infinity and infinity, but it penalizes negative values, but not make it to 0. The other one is parametric rectified linear unit, p-ReLU, proposed in 2015. So leaky ReLU, it's a slope. They put it 0.01. They didn't make it a hyperparameter, the slope of the negative value. There was another paper which made it a hyperparameter. Okay, so and they called it parametric rectified linear unit, p-ReLU. So the slope is alpha now, and alpha is usually a small number, right? There is also softmax. Softmax is very important. What does it do? So I have some outputs. First up, you tell me, when I have a bunch of values, okay, bunch of scalar values, I want them to behave like a probability. There are several techniques to do. What should I do? How can I make a bunch of values behave like a probability? When I say there is some the value is probability, it has at least two properties. One property is that it's between 0 and 1. Also, when there are a bunch of them, assume they should sum to 1. Let's consider a discrete probability mass function. They should sum to 1, right? So first off, each of them should be between 0 and 1. Also, they should sum to 1. So I have a bunch of values, make them probability. How do you do that? No, how do you normalize it? Exactly. So you divide each of them by the summation of all of them. So assume I have A1, A2, A3. I can say A1 over A1 plus A2 plus A3, then A2 over A1 plus A2 plus A3, also for A3, right? They sum to 1, and they are between 0 and 1. So they behave like a probability. However, let me add another request. I want them to behave like probability, but also like a Gaussian probability. How can I make it behave like a Gaussian probability? What was the formula for Gaussian distribution? Let me Google it. We don't memorize anything, right? This is right. Some normalization fact. Can I zoom to this? Some normalization factor, right? Times e to the power of something, right? This normalization factor makes it to become to sum to 1 or to integrate to 1. Okay. So basically, I have e to the power of minus something or e to the power of something, right? Because of this e to the power of something, it belongs to the exponential family. So we have an exponential family of distributions where all of them have e to the power of something. Okay. Gaussian distribution is one of them. Okay. Therefore, can I say when I have that A1, A2, and A3, can I say, let's make it e to the power of A1 to the e to the power of A1 plus e to the power of A2 plus e to the power of A3. Also, e to the power of A2 over e to the power of A1 plus e to the power of A2 plus e to the power of A3, and also for the A3. If I do that, it behaves like a Gaussian distribution. Agree? Because it sums to 1. They are between 0 and 1. Also, they have e to the power, so they are in exponential family, right? This is called softmax form in machine learning. Okay. So they are probabilities, but Gaussian probability. Okay. And by the way, let's go back to the formula of PDF of Gaussian distribution. No. Why isn't this normalization factor important to me? Why do I get rid of that? Only I care about e to the power of something here in softmax. Because I already make them between 0 and 1 by dividing with the summation of everything, right? Why do I need the normalization factor when I make them to sum to 1, also to become between 0 and 1? This normalization factor makes it sum to 1. That's another. So now we understood the philosophy behind softmax form. Okay. Let's continue. So this is softmax form, and what does it do? Usually it's used in the last layer of neural network when we have classification problem. Okay. Especially when we have multi-class classification. Okay. So why? Because in the output, then I'm assuming that I want to say that for some input, which class has more probability for this to belong to. For example, assume I feed the input to my input X to my network. It outputs, after softmax form, it outputs 0.1, 0.8, 0.001, 0.09. So I have four neurons at the end. When I say 4 neurons, I mean 4 classes. Right? So the number of neurons, the last layer, I set it to the number of classes. So I have classification with 4 classes. Okay. Of course, this probability is sum to 1 because of softmax form. They are between 0 and 1. Then I can say which one is the largest. This one, right? So that input belongs to class 2, the second neuron, right? So I can compare the values and say which one it belongs to. So I can use softmax form when I have multiple classes in classification. But what happens if I have only 2 classes, binary classification? Should I definitely use softmax form? I can use softmax form with 2 neurons. I can. But there's another option. When I have binary classes, I have 2 classes. There's another option. What other activation function can I use rather than softmax for binary classification? Yeah, choosing the maximum of output is always used for classification, okay, in the test phase. But I'm saying that I'm talking about the choice of activation function. So one option is to use 2 neurons with softmax form because I have 2 classes. Another way is to use sigmoid or logistic. Because when I have only 2 classes, I can have only 1 probability. Because the other probability is 1 minus that probability, right? Therefore, I can only have 1 neuron now and use sigmoid activation function at the end. Then it gives me the probability. I assume that this probability belongs to the class 1. So 1 minus that probability belongs to class 2. So whenever that probability is above half, it is class 1, less than half is class 2, or the other way around, depending on how I define it. Did you understand? So when I have classification with 2 classes, binary classification, I can either use 1 neuron at the end with sigmoid activation function or 2 neurons with softmax activation function. When I have multiple classes, I have to use softmax activation function. Another thing with softmax has a flaw. So by the way, this was for classification. What is its flaw? I just pointed to that. What is the flaw of softmax? This denominator. What if M is big? Don't see that in just neural network. It can be used anywhere, right? What if M is big? Calculation of this denominator, this summation, can become a pain in the neck. Can become intractable, right? So that's another thing. Actually, sometimes, even in neural networks, M is too big. The number of neurons is too big. When does that happen? Have you seen that? In natural language processing, in GPT, in ChatGPT. Okay. It's actually a neural network. Its output, we will see that. We'll talk about it, but its output, the number of neurons in the output layer is the number of words in the dictionary, in the Oxford dictionary, for example. How many words do we have in English? So the number of neurons is like that. Why? Because we want to see which word has more probability. For this string of the words, the previous words, what is the most probable next word? Okay, so I need to have the number of neurons as the number of words in the dictionary. So M can be big. So softmax is a problem, has this flaw. That's another thing. Also, softmax has something I want you to note. Softmax has some delight difference from other activation functions? Can you tell me? All other activation functions that we discussed, softmax has a difference, a big difference with them. In all of these other ones, every neuron is by itself. It doesn't care about other neurons. Every neuron in the layer, its activation value is calculated by itself. Doesn't care about others. It's selfish, right? However, in softmax, it's a collaborative thing. All neurons are contributing to the softmax. To the output of one neuron, you should see the outputs of all of the neurons. To calculate the output of the one neuron after activation function, you should see the outputs of all neurons before activation function. Did you see the difference also? Okay. And by the way, its derivative is this. Delta ij is a Kronecker delta. Kronecker delta is also used a lot in machine learning, also used a lot in modern physics. I don't know if you have seen the formulas and mathematics of relativity, general relativity, special relativity. Have you seen those? Okay, they use a lot the Kronecker delta a lot because this Kronecker delta is also used with Einstein's notation. Anyway, let's not go into the details. So the Kronecker delta is delta ij. If I and j are equal, it's 1. If I and j are not equal to each other, then it's 0. By the way, Einstein notation, don't worry, it's very simple. It says that when I have summation of xi and yi, okay, usually in physics, we have superscript and subscripts as the indices, okay? When I have this, one superscript matches another subscript and the summation is over I, Einstein was lazy and said, let's get rid of this summation and assume there exists a summation there. Okay, so xi, yi means summation of xi, yi. This is Einstein's notation in physics, okay? And as I think you can imagine why it relates to the Kronecker delta, okay? Anyway, that was in parentheses, okay. The other activation function is max out, proposed in 2013. It's basically, I don't have a lot of knowledge about it, but basically whatever I know is this. So what does it do? It takes the maximum of the outputs of the neurons. So for example, each of the neurons outputs something, then you take the maximum of that. This is max out. For example, 0.9, 1.02. So because they can be above 1, right? Anything or minus. The maximum of these is 3.01. And you can see that here for softmaxes, they sum to 1, but for max out, they don't necessarily sum to 1. You just take the maximum. And this is its derivative. What does argmax mean? Which index, which neuron maximizes that, right? So here, for example, maximum is 3.01. Assume I have 4 neurons only. Then argmax becomes 3, right? And these are the reference. Any question before the break? No? Okay, let's have a break and come back at 9:05. Okay, great. Okay, let's continue. And now we have talked about fully connected neural network or multi-layer perceptron. Let's start backpropagation and optimization of neural network, training of neural network. Okay. First, gradient descent. So basically, I just let you know, spoiler alert, that backpropagation is nothing but gradient descent and chain rule. Okay. And so we need to talk about gradient descent a bit. Gradient descent is one of the fundamental first order methods. So do you remember we talked about this? When I have an unconstrained optimization problem, I take derivative, right? Then you take derivative, set it to 0. Hopefully you can find a closed form solution. If not, you need to use numerical analysis, numerical computation, and do it iteratively. So you then, depending on whether you use first order derivative or both first order and second order derivative, you will have first order optimization or second order optimization. There are a lot of algorithms in first order optimization and a lot of algorithms in second order optimization. The most famous one in the first order optimization is gradient descent, right? It's like going down a mountain. Gradient ascent is like going up a mountain. So it was first gradient descent. It was first suggested by Cauchy. Did you know that? By Cauchy in 1874. How old is it? And Hadamard in 1908. Its convergence was later analyzed in reference 3. Okay. So consider this unconstrained optimization problem. Minimize f of x with respect to x. A numerical optimization for unconstrained optimization, we start with a random feasible initial point and iteratively update it by some step delta x. Okay. Then xk plus 1 becomes xk plus delta x. So we continue until we converge or get sufficiently close to the desired optimal point, x star. Agree? This step, delta x, is also denoted by p in the literature sometimes, especially in the literature of pure optimization. They denoted by p also. So p or delta x. Now we want to prove gradient descent. We'll see. I guess we proved that. Do I? I don't remember. At least in my optimization course, I proved that. Here, do I prove? No, here I don't prove that. Sorry, it was too complicated. I removed that from this course. But we can prove gradient descent. Okay. For more information on that, see my optimization course on YouTube. So assume the gradient of function f of x is L smooth, where L is a Lipschitz constant. What is L smoothness? Did I talk about it in preliminaries? No? Okay. So nothing very complicated. In L smoothness or Lipschitz continuity is used a lot in optimization. It basically means an upper bound on the slope of function. Do you agree that at every point our function has some slope, right? Going down or going up some. And by the way, this slope, if it is multiple dimensions, you can consider it as the slope of the tangent space. Like consider it as a surface, and on the surface or this manifold, you have a tangent space, and this tangent space also has some slope, right? So you have some slope at every point in the function. Now assume I have an upper bound on my slope. For example, consider this function. So here it's a slope. Here it's a slope, a slope, a slope, 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 slope. Maybe the biggest slope is this, right? So this or a greater value is the L for my Lipschitz continuity. When I say L smooth, I mean my slopes, all of them, are all less than or greater than L, something like that. Okay. On the whole domain of my function, the whole feasibility set. So now, why is it important for optimization? Can you tell me? Why is L smoothness or L smooth, L continuous? They're all the same name for different names for the same thing. L smoothness or L continuity. Why is it important? Can you tell me in optimization? According to what I just told you. L is an upper bound on the slope. Why is it important for optimization? What happens if L is big?
Gradient of X.
Yeah, the gradient becomes very hard to calculate. Actually, it's kind of a measure of hardness of my optimization problem. How hard is it? For example, consider this. Assume I want to minimize this function, or equivalently, I want to maximize this function, doesn't matter. I want to maximize this f with respect to x. Do you agree that this is very hard to maximize? What is the slope of this function, the maximum slope? It's infinite, right? Here, the slope becomes infinite. So it's very hard to optimize to find this. What is the maximum of this function? It's infinite. And the arg max, I don't know if it is defined, but assuming that it is defined, it is 0. Okay. So, but if I want to solve it iteratively, it's very hard. Actually, gradually the gradient explodes, right? That's the reason that you see L smoothness a lot in optimization literature, because it shows you how hard is your cost function, right? And in the proofs of many of your optimization algorithms, you see the parameter L. Okay.
It's the same about Lipschitz.
Lipschitz.
Yeah.
This is Lipschitz. Yeah. When I say L smoothness with parameter L. Lipschitz continuous or Lipschitz smooth with parameter L. And that parameter L is the max upper bound on the slope of function. Okay, agreed? Understood? So, as I said, for more information, see my optimization techniques course. But if you see that course, you will see that in gradient descent, this is the step. This must be the step. Minus 1 over L times gradient. What is L here? L is the Lipschitz constant for gradient of function, not the function itself. So the function has some gradient. The gradient of function is another function, agreed? The gradient of function is another function. That also has some slope. That also has some upper bound on its slope. So assume the gradient of function is L smooth. Okay? Then my step in gradient descent becomes 1 minus 1 over L times gradient at that point. And this is my current solution in gradient descent. So my next solution will be my current solution with this step. Okay. However, there's a problem here. How can we calculate this L? It's actually hard. Calculation of L itself is very hard because you need to go on the whole range or domain of function and see the slopes, all of them, and take the maximum. We know that the maximum slope is the lower bound for L. So upper bound of the slope is a lower bound on the L, because L is an upper bound on the slope of function. I think it became a bit complicated. Assume your slope is its maximum is 1000. L is greater than or equal to 1000, right? So you have to go across the whole domain, and calculation of L is a pain in the neck. Therefore, let's replace 1 over L with some eta. Let's approximate. Okay. Then delta x becomes this, minus eta gradient of f. And we call this eta step size, also called learning rate. Right? So, yeah, as I said, we kind of are approximating the gradient descent. Okay, but by replacing 1 over L with eta. If the optimization problem is maximization rather than minimization, then the step should be eta rather than minus eta. Then we call that gradient ascent. It's like going up the mountain rather than going down the mountain. Okay. By the way, the learning rate can be found by line search. I think I have talked about line search here. Let me check a bit. I might not. I don't remember. Well, if I have talked, we'll see that. Okay, doesn't matter. So let me briefly tell you what line search is. For more information, you can see my optimization techniques course on YouTube. So line search, basically, another question arises here, that what value do we choose for eta, right? Of course, it shouldn't be a too big value. It should be small. But how much is small? So we can say, let eta be a big number for now. Why do I desire this to be big? Because the bigger the eta, the bigger my jump, the faster I get closer to the optimization solution, right? To the minimum of cost function. So the bigger the eta, the larger the eta, the faster my optimization converges. Therefore, I desire this eta to be big, but there is a trade-off. When I make the eta big, it becomes inaccurate. Okay? Especially assume you set eta to a fixed number, okay? Initially, a fixed big number. Initially, it's good for you because initially you are very fast. But gradually, when you reach around your solution, you jump around it. You never reach that because your steps are not fine enough. They are coarse steps. But now the other way around. What if I set eta to a fixed, a small number? What happens? Too slow. Even initially, it's too slow. Okay. So sometimes in the literature, they set adaptive learning rate. For example, they say, let it be big learning rate and initially, and then gradually I decrease the learning rate. Because gradually I am assuming that I'm getting closer and closer to the solution. And around the solution, I'm not supposed to jump and oscillate. Okay. But in gradient descent, rather than this adaptive learning rate, we can do another thing, and that's called line search. Line search says that at every iteration of gradient descent, let it be big, consider eta to be a big number, and then see what happens to your next solution. Don't update your next solution yet, okay? Calculate the cost at this update, the next solution, the supposedly next solution. Calculate your function cost value at the supposedly next solution, okay? See how much is it. Is it less than the cost of the previous solution? If yes, accept that eta, right? Because we want the cost to decrease. If not, halve the eta or decrease the eta. They usually halve it, okay? Then do this again. Check this decrease eta until this is satisfied, until the function, the cost value of the next solution becomes less than the cost function of the previous solution. Clear? This is called line search. By the way, we have variants of line search. One of the simplest one is backtracking line search, also called Armio line search. Armio is written as this. Armio line search, okay? Or backtracking line search. There are other types of line search, such as Wolfe condition. By the way, I'm saying these in parentheses. These are not related much to deep learning, but I have talked about these in detail in my optimization course. Wolfe was a great scientist in optimization. You hear his name a lot in optimization. So Wolfe condition added another condition named curvature condition to Armio condition. So Armio condition and curvature condition both together become Wolfe condition, and they usually use Wolfe conditions for line search in second order optimization, such as Newton's method, such as interior point method. Okay. Or specifically, they use that a lot with, I don't know if you have heard of LBF BFGS algorithm. Have you had? Just Google it later. BFGS optimization method. That's for second order optimization. Okay. Anyway, that was in parentheses. Now, for a convex function, what do I mean by convex? You know? No, convex function. So basically, in simple words, a convex function is like a ball, okay? With one bottom. When it has more bottoms, multiple bottoms, then it's not convex. Basically, whenever I can say like this, so this part is out of the below the function, right? When I can do this, where some part is below, some part is above, then this is a non-convex function. Convex function, as you see, when I connect every 2 points, all of these is below. Okay. Whenever I have a convex function and I want to optimize that, I'm very happy, because you should be very lucky to have a convex function to optimize. Okay. Then in this case, you definitely know that you always get your cost decreases. It's like you're going down a bowl. It's very easy. But what if it's not convex? You don't. Sometimes you might oscillate. You might go up a little bit and you go down. That's why in deep learning, as the cost function is usually non-convex, you have some oscillation, but usually the overall pattern goes down. Okay. So here, as I'm showing, when it is convex, the cost always goes down smoothly. Otherwise, you might have some oscillation like this. And you see that a lot in deep learning. And I think it's obvious, because in the cost here, when it is convex, you're going down always. But when it is non-convex, you might jump here, which goes up a little bit, and then go down again, right? Now, what if you have too many iterations? Then you will see something like this. It oscillates, but the overall pattern goes down, right? But if it is convex, you will have a smooth plot. By the way, a question, a puzzle. Why in neural network is the cost non-convex usually, highly non-convex? But this is a good puzzle. If you understand this, you have understood deep learning very well. Assume my loss function is minimized summation I from 1 to b, where b is a batch size, some number of points, yi minus yi hat squared. Yi hat is the output, predicted output for xi, predicted output of neural network for input xi. Yi is the actual label. This is a mean squared error, right? I'm minimizing the mean squared error. Do you agree that what is this? This is actually, if you consider it as a vector, this is a squared L2 norm, right? The squared L2 norm is quadratic, right? Like a bowl. This is bowl or quadratic function is completely convex. Then why do I say that usually cost function of the neural networks are highly non-convex? Actually, when you see the cost functions of neural network, they're like mean squared error, they're usually like these very simple functions. Then why am I allowed to say that the cost functions of neural networks are too complicated? If you can visualize them, there are a lot of valleys and peaks in the optimization landscape of the neural network. Why? No. But let me know your answers. That's fine. High dimensions, that's another thing which I will talk about, but that's not the answer of this question. Why, although I'm using this simple function, why am I saying that my cost is highly non-convex in neural network? If you see the cost function of neural network, you will get scared. It's very complicated. What?
Not all the points fall on the same time. And there is a lot of irregularities in the error. So talking about the generalized solution to an optimization problem. So that generalized solution, if we account for all the data points, it becomes a lot of skew. That is why it has a lot of variance.
So you are saying that when we consider this for all of the data points, a lot of data points, then it becomes non-convex? I disagree with you, because this doesn't matter of the size of B. Doesn't matter. Use 1 million points in this function, it is convex.
Discrete optimization.
No, it's not discrete optimization, but it's good that you're thinking. Let me give you a hint. This is convex with respect to what? No, this function or this function is convex. So its variables are yi and yi hat, right? So it's convex with respect to, or each of them also, the difference or each of them, yi hat or difference, okay? It's also convex with respect to each of them. Convex with respect to yi, convex with respect to yi hat. Yi is the actual label, so yi hat maybe is important. So it's convex with respect to output of neural network. What is my optimization variable? What is my optimization variable? Is it yi hat? What is the thing that I'm learning? Is it the output of neural network? The weights. We might have a lot of weights, yij's, a lot of weights, maybe 1 million weights. Is this function a convex function with respect to the weights? Of course not. We have too many nonlinear activation functions, too many linear projections, dropout, so many things. We have a lot of things going on in a neural network, and then it outputs something. This is convex with respect to the output, not the optimization variable, right? That's the reason that the cost function of neural network is highly non-convex. Okay, we talked about this. Convergence criteria. Okay, for all numerical optimization methods, including gradient descent, there exist several methods for convergence criterion to stop updating the solution and terminate. When do we terminate? When do we end gradient descent? Okay, some of them are these. Small norm of gradient. Why? Whenever the L2 norm or any norm of gradient at that point is less than some small epsilon is a small positive number maybe, I can stop. Why? Can you tell me? So there is a reason behind everything. Why? Recall, what do we do whenever we want to find an extremum or minimum or maximum of a function in high school? Take derivative, set it to 0. Why do we set it to 0? Because the derivative at the minimum is 0. The derivative is gradient. The gradient is 0 at that. But derivative is a scalar, gradient might be vector. So we say L2 norm of gradient is 0 at that point, right? So when norm of gradient is a small number, it's close to 0. So we are probably at the minimum, okay? But it has a flaw. It has a flaw. What is the flaw of that? Consider this function. So I'm going down. I'm going down from here. If I do that, I will stop here. So it might get stuck in the, you tell me, in the saddle points, and local min. So two flaws. Saddle points like this, and local minimum, right? However, local minimum is not much a big deal, I will tell you. It's related to what you said about dimensionality. Okay, according to the theory of neural network, if you go, so you can analyze the neural network with pack learning. I don't know if you have heard of pack learning or not. Just Google it. Pack learning. Pack learning is short for probably, approximately correct learning. Okay. So what do they do in pack learning? They try to find probability bounds for the errors of the machine learning model. You can find the probability error for the generalization and performance of the neural network optimization. Okay. There are theoretical papers on that. For example, there is a theoretical paper on analyzing the optimization of neural network published in IEEE Transactions on Information Theory. Okay, so this is very theoretical. And they discuss that usually in the cost function of neural network, usually all of the local minimums are good representatives, and there you can see them as global minimums. So it kind of, it's like this. All of them are almost in the same range. They might have some difference, but whatever local minimum you find is usually good. Not always, I'm saying that. Usually good. What is the reason behind that? Roughly speaking, it's because of this. When we have too many layers, it's like you're transforming data from the input space to some other space, such as Hilbert space. Okay. In that Hilbert space, usually all of the local minimums are good enough. Okay. So because of this transformation and a lot of dimensionality that we have in a lot of weights, usually local minimums are good enough. That's why usually nowadays we don't care about the initial, usually I'm saying that, about the initialization of your weights. Whenever you start with any initialization, whatever you end up usually is good. Unless something happens and you need to retrain it. But usually it's good. That is the reason. Okay. So what were we saying? Another convergence criteria is when the difference of the costs don't change much. Right? Okay. Another one is that when the difference of norms, right? L2 norm of norms is less than epsilon. Agreed? Because the gradient hasn't changed much. It means that the slope hasn't changed, right? The slope hasn't changed much. Another one is maximum number of iterations. We use that a lot in deep learning, right? We say train it for 1,000 epochs, for example. Epoch is the number of iterations. Oh yeah, I have talked about line search. So we saw that the step size of gradient descent requires knowledge of Lipschitz constant, right? For the smoothness of gradient. However, we may not know the exact Lipschitz constant. As I say, it's very hard. So let's find it by line search. In line search of every optimization iteration, we start with eta equals 1, so big eta, big number. And then we check whether this is satisfied or not. What is this? The cost at the next update with this eta. Does it decrease? Is it less than the previous cost? If yes, accept that eta and accept this delta x with that eta. Otherwise, halve it, decrease it. Okay. When you do this, you basically are searching for an eta which is less than 1 over L. You don't know the value of Lipschitz L for smoothness of gradient or function. You don't know that. You start from some eta, you decrease it until eta becomes less than 1 over L, because we know that 1 over L is the actual eta that we are looking for, right? This is called Armijo line search. Armijo was also a great scientist in optimization. You see his name a lot across optimization. Armijo line search, also called backtracking line search. Another more sophisticated line search is Wolfe conditions. For more information, see my course, optimization. Let's see gradient descent algorithm with line search. So initialize, by the way, this is not just for neural network, any gradient descent, right? Initialize the solution, x0, it's a vector, right? For iterations, so you have it, it's an iterative optimum. Then initialize eta to be 1 at every iteration, right? Then here, what am I doing? This is line search and update both together. So I check the line search condition. What was that? Whether the cost of the next solution is less than the cost of previous solution with that eta, right? If not satisfied, halve eta. Otherwise, update the solution with that eta and break the loop. Come out of the loop, go to the next iteration. Again, start with eta equals 1, right? Also, before going to the next iteration, check the convergence criteria. And if it is converged, then return that solution. Okay? By the way, as it is shown here, line search has its own internal iterations inside every iteration. Therefore, you have nested loop here, right? Now, momentum. We can have momentum with gradient descent, okay? In gradient descent. What is that? Gradient descent and other first order methods can have a momentum term. Momentum proposed in reference 6 makes the change of solution delta x a little smaller, a little similar to the previous change of solution. What do I mean? Do you remember what was the previous, what was simple gradient descent? Let me add a new page. X was x minus eta gradient, right? Agreed? Let's call it delta x. So it was the xk plus delta x k. Agreed? This was in simple gradient descent, delta xk was minus eta gradient. But when I have momentum, I assume this delta xk is this minus eta gradient of f of x plus some other term. That is alpha times gradient, sometimes the previous delta x. Okay. So here I'm adding some weight of alpha is some weight, right? Some hyperparameter, some weight of the previous update, adding that to my current updates. What am I doing by this? What is the philosophy behind it? When I do this, I have less oscillation. What do I mean by this? Consider this cost function. Without momentum, my gradient descent might go like this. Like, do you see this? These arrows? They are small. Do you see them? They are like this. Right? Going toward the minimum. However, when I have momentum, I have less oscillation, something like this. The reason in English language is because I'm adding a log of my previous memory. So I a little remember my previous memory. This is in English. Now in mathematics. Assume you were going by gradient descent, you were going like this, right? But the previous delta x was like this. So I'm oscillating, right? I'm oscillating. I'm currently here. My previous delta x was like this. So this is my minus eta gradient of f. Now, starting from where I am, this is my previous delta x, right? Agreed? What is a linear combination of them? This previous delta x pulls this toward itself. A little here. A linear combination becomes here. rather than going too much in an oscillated way, it comes a bit. So it's mathematically speaking, and English speaking, it's because I'm using the memory. So I'm trying to remember my previous way, right? So I don't oscillate from that a lot. Agree? This is momentum. We see that a lot in optimization. Okay. And as I said, this alpha is a momentum parameter. We can use momentum in optimization of gradient descent as this is neural networks as well, deep learning. Okay.
This make the optimization more stable.
Yeah, kind of. So it dampens the oscillations a bit. Okay. It makes the kind of optimization more stable. I agree. Now a steepest descent. Steepest descent. Sometimes people in the literature they use them steepest descent and gradient descent interchangeably, but it's wrong. They are different a bit. Steepest descent is similar to gradient descent, but there is a difference between them. In a steepest descent, we move toward the negative gradient, like gradient descent. In gradient descent, we are moving toward minus eta gradient, right? Negative gradient. In a steepest descent, we do the same, but as much as possible to reach the smallest function value, which can be achieved at every iteration. What do I mean? If I want to depict that, like this, gradient descent, for example, goes like this. A steepest descent goes like this. Okay? The steepest that it can go. So, argmin with which eta this becomes minimal. Okay? Then it finds this eta and uses that for optimization. Agree?
Same as we increase the step size.
So yeah, so for a steepest descent, you don't need to do line search because it finds the eta. But the steepest descent has more computation than gradient descent because in gradient descent you don't need to do this, right? In a steepest descent you need to find which eta makes it minimum. We usually use gradient descent because I think we are lazy. Back propagation, but I'm not sure whether we can cover it. Yeah. Let's start back propagation in the next session. But before we end, let me tell you that back propagation is nothing but gradient descent and chain rule because we have a stack of layers and each layer. So when we have forward propagation, when we feed the input to the network, it goes layer by layer from first layer to the last layer. But when we want to train it, we want to optimize it. We go from the last layer to the first layer. Why? Why do we go from the last layer to the first layer? To minimize the error, and the error is dependent on the output of the neural network. So we have to go from output to the input, right? So we do that. That's what, hence the name back propagation, because it back propagates backwards. Okay, and as you can imagine, the weights are dependent on each other, so you need to have chain rule. Okay, and we will prove chain rule in a simple way. This is the simplest way that I have found to explain back propagation, and its credit is for Professor Ali Qudsi. He explains it very simple. Okay, and I explain it in the same way to you, and I think it's the simplest way. Otherwise, there are some very complicated explanations of back propagation which might confuse you. This is the simplest way. We will talk about it in the next session. Any question before we wrap up? No? Okay, thank you.